Nuclear Criticality Safety Practices Instrumentation from International Nuclear Atomic Agency, link in the description below. It might seem that warning of an accidental approach to criticality could be given by a neutron detector and an appropriately placed neutron source such as those used for subcritical confirmation by in situ multiplication measurements. If so, conditions might be corrected before the radiation level becomes dangerous. It is rare, however, that plant process conditions are sufficiently favorable and stable for meaningful indication of increased neutron multiplication before delayed criticality is attained. The warning probably would be too late except to signal personnel evacuation. Certain indirect methods of criticality control that depend on the properties of fissionable isotopes make use of specialized radiation detectors. In gaseous diffusion plants, for example, accumulation of 235 uranium has been identified by measurement of characteristic gamma radiation from 235 uranium, thereby allowing detection of growth and removal of an accumulation before it becomes dangerous. Also, the absorption by fissionable material of gamma rays or neutrons directed through a process stream depends upon the chemical concentration of the solution and can be used for concentration control if there is a suitable source and detector. Another method makes use of the high spontaneous fission rate of the 240 plutonium isotope, which accompanies 239 plutonium in a proportion characteristic of the material history. The neutron background in a plutonium process is therefore a measure of the plutonium concentration, and a change in an established background can signal an abnormal condition in a process stream. Because of this effect, surveys with neutron detectors can establish the location of unplanned plutonium deposits, a technique that could have prevented the Los Alamos accident. These indirect methods of criticality control are empirical and must be based on the calibration of appropriate instruments. The instrumentation for identifying fissionable isotopes have become highly sophisticated as a result of material safeguard requirements. Detectors have been so refined that quantitative measurements of the various isotopes of uranium and plutonium and certain transplutonic elements in low-density accumulations are practical by detecting characteristic gamma ray and fission neutrons. Application of this instrumentation to scrap and to waste disposal reduces uncertainties in their fissile content, thereby providing better criticality control and minimal inadvertent loss of material. Other safeguard instrumentation is capable of providing nearly continuous monitoring of process streams. The absorption of gamma rays in high-density materials such as uranium metal, compounds, or fuel elements interferes with their direct diagnostic use. Consequently, the so-called random source interrogation technique has been developed for measuring the 235 uranium content of this type of material. In this method, fissions are produced by neutrons from an external source, usually AMLI because its neutron energy spectrum is below the 238 uranium fission threshold. Neutrons from fission are detected in the presence of source neutrons and gamma rays by coincidence counting, and the rate of coincident events is a measure of the 235 uranium content. This technique is useful for confirming the content of core miners in storage or use between processing stages. Instruments for the detection of radiation are also useful in accident alarm systems to signal evacuation in the event of criticality accident. The value of these systems has been clearly demonstrated as well as will be seen in Part 3. Gamma ray detectors are usually selected. Reliable instrumentation and freedom from false alarms are more important than sensitivity. The requirements on such instrumentation are addressed in American National Standard Criticality Accident Alarm System.